right, welcome back to your last week of school for the rest of your life, unless you have any sense whatsoever and are going on to some other professional program. Like medical school, dental school, that's if you're unoriginal, sorry. You could get a PhD. I told you that, we just don't have enough people applying to chemistry and biology grad schools. You still get to be a doctor, we pay you to go, and if nothing else works out for you, apply next year. Obviously, it's too late right now. So, this is, I'm guessing this is our last lecture. What I'll try to do is to film the review session, which will be very long. I mean, it's going to be pretty long, at least 2 hours, so it'll use up the whole Friday. Except that I'll release it early, right? So, let me get the timer. I'll release it early, and let me also state that the final should be in about a week and a half, and that's 2 hours long, like normal. The final will be exactly the same format as all the other exams, except that it's comprehensive, and not to, sorry, but that's how we do it. And, I can't make it easier on you than what the people in Northwestern and University of Chicago were getting, because if you're weaker than them in terms of your preparation, they're going to step all over you, because they got something you don't. They already have money, and they already have connections. You have to outperform them, and you have to outperform them in a big way, because they've already got every advantage that they could possibly have. The only one you have is to actually be more useful than they are. So, anyway, think about that. Okay, so last week of school, again, your exam is coming up. If you are asking yourself, like, what is that Maxwell-Boltzmann thing? How does Planck work? Then you're really far behind. I would say that if you don't remember those types of things, then you're probably locked into a C for the final, which means that's not going to help. That's probably not advancing anyone's grade. So recall that the problem is that if you're going to try to study at the last minute, then by definition, you're doing it for everything. If you're doing that for everything, then you're trying to put into your head too much at once. If you're going to study for, let's say, 5 hours for every class, why not go ahead and spend some of that time right now? What does it matter when you do it? It does not matter when you do it, because you're going to do it no matter what. So you might as well go ahead and start studying right now. Because if you start now and spread it out, at no point are you trying to stuff in too much at once. Then it has a chance of getting in, right? All of this actually makes sense. The only question is, do you do it? The only question is it going to be an A or a C? All you've got to do is spend the same amount of time now as opposed to later. But those who do, you say something about your character, you're going to do well. Those who don't, well, you're not going to do well, but that's just who you are. But you do have the ability to make a choice, no matter what the producers of Westworld say. I just watched the whole series. Anyway, okay, so let's talk about stuff I'm actually supposed to talk about, which is enzyme kinetics. So I'll really get into some biology today, and I do feel bad that they really don't have any opportunity to talk about physical chemistry for biochemists. What does that mean? It's a hydrogen, we're doing quantum mechanics of hydrogen atom. Well, when it comes to kinetics, I can finally bring up some of it. And remember, I told you that I do kinetics last because it's really way easier than this other stuff. And I know that you're chomping on the bit to get out of here. Okay, when it comes to enzymes, I'm not really a biochemist, but I'm kind of interested in it. Cancer runs in my family, and enzyme kinetics has a lot to do with cancer. So you have enzymes that do digestion of proteins. Those are proteases like pepsin. I think there's another one, capsaicin or something. I don't know that much about it. I know they exist. The real important ones are the phosphotransferases, and especially the tyrosine kinases. Those are the ones that are signalers, and they signal, like tyrosine kinases. I think those are like phosphorylate tyrosines on proteins that sit on the surface of cells. When they do that, what happens is they change the structure of the protein. And that's how you transmit a signal. Now, it's a membrane-bound protein, so it transmits the signal to the inside of the cell, and that's like a go switch for the cell to start growing. Now, that's fine and good. You need your cells to grow, or you'll die, but you shouldn't be doing it all the time. So what happens is, if the go switch gets stuck on the on position, that is literally the definition of cancer. Now, your DNA is also generally pretty scrambled up too, but it's two sides of the same coin. So there you go. I just wanted to bring in the horror. Oh, and then matrix metalloproteases. Those are called MMPs, and what they do is that when a tumor is somewhere in your body, there is a lot of tissue that surrounds it. I mean, there has to be, right? It's inside of you. What the MMPs do, they'll break down that tissue. Now that's bad, because that's going to allow the tumor to spread. When a tumor is spread, you are now at stage 3 or stage 4 cancer. Stage 1 and stage 2 is when the tumor is localized. If the tumor is localized, again, of course you have cancer. If the tumor is localized, your odds of survival are quite good. They're going to just cut it out. You're cancer-free. If the tumor has spread, because the MMPs have done their work, they've broken down the area around the tumor, allowing the tumor to break apart itself and fly around your whole body, then you're at stage 3 and stage 4. At that point, your odds of survival are only around 10%, because they can't cut it out. What's the point? You know, surgery is really invasive. If you go through surgery, it's going to really knock you down a couple of pegs, especially if you're in your 60s or 70s or 80s. You can't recover from that easily. And what's the point? If there's a big tumor, they cut it out. Well, they got 20 more somewhere else. They're just waiting to grow. There's no point in cutting any of them out. It's not going to work. That's why you go to chemotherapy. So MMPs have a lot to do with that. And they have metal, they have zinc, and the zinc is like a catalyst for breaking down the area around the tumor. So ultimately, all of these enzymes, what they do is they take some kind of substrate, and notice I'm using kinetic language into some kind of product, even if that product is just like a digestate. Anyway, so there you go. Last thing about MMPs is that they're very upregulated in cancer. So when your tyrosine kinases are on the on position all the time, making everything grow, these things are also, there's like way too many of them, which is helping your cancer grow. So let's see, what I want to talk about next is the study of proteins is called proteomics, and so you'll always hear this term if any of you get into the biomedical community, especially in the research community. You're going to hear activity-based proteomics, which is how active are these enzymes. So here's a little funny thing I've noticed. Whenever I do any research with an enzyme and my nanoparticles, this slays me to this day. It's like I want to know how many grams or how many moles of enzyme I'm buying from a chemical company. They never tell you. They tell you units. What they're telling you is the activity, how active. So the thing is, they don't know. They don't know how many proteins, how many enzymes they're selling you. They just know the overall activity, which is related to the number, but is not directly, it's not necessarily one for one. Now the reason is that in the isolation of some of the enzymes, they might mess some of them up. And so they don't want to tell you that there's 1 mole of enzymes when half of them are defective because just something happened. So they tell you basically how much they produce in terms of their activity of taking substrates to products, and that to a biochemist should be good enough. Okay, so that's what activity-based proteomics is. Now, the concept of protein activity, that came from this guy, Henry, who, you got to remember that about 1900, He was one of the first people to start looking at kinetics, and what he did was he started writing down those rate laws. dp dt is equal to yada yada yada, right? The rate law or the rate expression, two things for the same thing. He is the first person to start thinking in terms of what's dp dt. Now, what's kind of neat is that, so he said basically activity is proportional to the change in the products over time. And the funny thing is that he just stopped there. He never like integrated the rate expression to the integrated rate expression. So he never cared about, you know, what is P of T. He didn't care. That was, he just did this part, and that was enough for him. But remember, this is like the first time anyone's figuring any of this out, so I think we can cut the guy a break. Okay, not too long after that, and these two people are famous. Lenore, it's a name you don't hear very often. Let me help if I can spell the name. Lenore, Michaelis, and Maud-Menten. I think they were at the University of Toronto, and this is 1913. These two were the first people to start really looking at enzyme kinetics and describing it. Now, so I'm going to derive all that. They made kind of a mistake. Well, it's not a mistake, it's like an interpretation that a lot of people don't accept anymore, and another group came along and reinterpreted their results. So I'm going to show you both. I'm going to show you their original supposition, which goes like this: an enzyme plus the substrate will form a complex. So that's K1, and I'll do backward by K2. And so there's this enzyme substrate complex. And then remember that enzymes are catalysts. So they turn the substrate to the product like way easier. The substrate may not ever turn into a product on its own. Just like the flesh around a tumor won't just fall apart on its own. The catalysts help it along. So KCAT will form, the enzyme will be released, but now of course we have a product. Okay, so this was their idea. And what they assumed is, so the thing that allows them to do some derivations is an assumption. Now this is the assumption that will later be kind of thought like, nah, not quite. So just heads up on that. Okay. They assumed that, hold on, let me little bullet point, right, bullet point. So they assume that there is an equilibrium. So, okay, they assume that there's an equilibrium between the enzyme and the substrate, and therefore, the way they describe that, now that is a capital K, right? Little k's for rates, big K's for association or dissociation constants, equilibrium constants. Now I'm going to write a dissociation constant. That means that I'm going to start here and go backward to there. Now that means that you know that you put for a, well, we've talked about how to do this in terms of rate constants. So let me remind you, we talked about this last time. But if you remember your freshman chemistry, you should know that will be products. So this is dissociation. The products are on top, and the reagent is on bottom. And there you go. Okay. So now you may recall that you can now manipulate this and say that, and you know, KD would be something that can be measured, so that the concentration of substrate, concentration of the enzyme is KD times the complex, the substrate enzyme complex. Okay. All right, now this is how they set this up. So I'm going to go ahead and solve, you know, here's the funny thing. It's like the integrated rate expression, but I'm never going to integrate anything, right? So that's where there's a little bit of an issue. So what do they do? Sorry, I gotta think about this. Okay, one of the things they assume, another assumption is a lot of substrate. A lot of substrate compared to the enzyme, and that is called, that's important, that's called the free ligand approximation. And this is something that is like important when it doesn't work. And when you read papers, that's like one of the things they want to characterize. Okay, now if you assume this, then you can state that the enzyme concentration would be whatever is in the body initially minus the enzyme bound to the substrate. That's the idea. Okay, so let's see here. Now what can I do? What I'm going to do is I'm going to multiply each side by S. Okay, now why am I going to do that? That's because right up here, E times S is KD times the E times S, I wrote it in reverse, is the dissociation constant ES. And ES is kind of important because this is going to be related to the product. Remember that the activated substrate enzyme complex, the rate of that, the kcat rate, concentration of that, is how you get products. So I really want to try to figure out what this is. That's our end goal. Okay, now from this sucker, what I can do some algebra. So I'm going to bring the KD ES over to one side. And then I've got, let's see, I've got this term here, and let's see, then I'm going to set the other term on the other side, which is S, and the initial amount of enzyme. Okay, so I've just done some algebraic rearrangement. Now, hopefully you see why. I can factor the enzyme substrate concentration out, and now I can set that equal to the right side. Again, E0 is the initial amount of enzyme, and then I've got that KD plus the, okay. So there you go. Now again, the reason I did this was because if we want to talk about the activity, right, activity-based proteomics, we want to know what dP dt is, and that is kcat times the bound substrate. Now that's just from our description of the mechanism, and therefore, remember that this is the rate. Therefore, the rate is kcat, initial concentration of enzyme, concentration of substrate, that makes sense, over, oops, let me do it this way, KD plus S. So you can see how I just inserted this. Now the reason I did this in a little funkily way is because this ends up being called the max. That is, the idea is that's the fastest the enzyme could possibly react. So the fastest that the enzyme could react is if it had like an infinite amount of substrate. So as soon as the enzyme spit out a product, a substrate's right there, and it's going to go again. Now notice that that would be if S is very large compared to KD. So let me rewrite this just so you get the whole thing. So again, if the concentration of substrate was like, super, super high, then you would have S on top, S on bottom, the KD wouldn't matter, and the rate would be the fastest possible rate, which is the rate of catalysis times the initial amount of enzyme. And so that would also imply that all the enzyme is tied up. Okay, so what you can do is graph what you call the, this is kind of a funny name, reaction velocity. That's just like when I Googled it. I actually put this mostly together from Google, to tell you the honest truth. The biochemists asked in our department, asked that I make sure that I covered all this, because they said, if you go to grad school in biochem, they actually don't talk about this. They assume that you had it in your undergrad. So they said to me, make sure you cover Michaelis-Menten kinetics. So anyway, so I gathered a whole bunch of sources to try to make this as coherent as possible. Okay, so here's the reaction velocity, or the rate. So I just thought it was funny that they call a rate a reaction velocity, but they tend to do that. I hate it when they just make up, new words for things that already have words. And let's see. What happens is, again, this is the concentration of substrate. Now, again, the rate as you increase the concentration of substrate will get closer and closer to the maximum that the enzyme could ever function. And it turns out that at the max over 2, so I'm like halfway, that happens to be where KD is, right? If you see, right, if KD is equal to the substrate, then you've got basically one half. So there you go. So that's Michaelis-Menten, and it turns out that the reason that this was such a big deal was just the first time anyone ever thought to do any kind of analysis and describe all these things. The concepts, especially that of a maximum rate, I still see biochemical things described with the maximal rate of enzyme, catalysis. So these concepts live to this day. However, there was a change of interpretation. Briggs-Haldane, a few years later, are going to derive basically the same thing. Now I'm going to show you the derivation. They derive the same thing, but they use the steady state approximation. Remember that from last week? They use the steady state approximation, and that means that they're going to reinterpret how this works. Now it turns out that their interpretation is kind of like the dominant one, so I want to show you that. The other thing I want to show you is a last time that I'm going to show you a mechanism, rate expressions, and then we're going to integrate those rate expressions. So I will definitely have something like this on the final exam. So you've already seen many examples, especially last two lectures, example after example after example. But because we're doing this before the final, one, if not two questions on the final will come from today's lecture, because why else are you here? So let me wipe out the board, because this next part is, by the way, this is going to be a little unpleasant. This is going to be the hardest kinetic thing that we've ever done. So let me wipe out the board, I'll be right back. Okay, so the Briggs-Haldane reinterpretation of Michaelis-Menten enzyme kinetics. So it is going to be looking very similar, where we have an enzyme plus a substrate, and it will go back and forth with an enzyme substrate complex, and there's still a K-cat. Here's a K2. K2 is backward, K-cat goes to products. So notice that, again, you can tell that I'm not just writing products and reactants, because I have all these intermediates and I have a bunch of Ks. So that's one of the ways you know that I'm not just writing the stoichiometry, I'm writing the actual mechanism. Now, if I've written the mechanism, you should be able to write the rate expressions, or the rate laws. So let's write the change in concentration of the enzyme over time, and hopefully this is going to be very easy at this point. Your sink is the enzyme itself, and it also is going to depend on the substrate. So it's actually going to be both of them, because without the substrate, the enzyme won't react. Okay, and remember this is a second order. That's a second order type. A plus B goes to C. We covered that on, I think, the first day of kinetics. So you've actually seen this before. And this, again, is the second order. It gets a little bit more complicated because it goes backward. And the agent for that reformation is the enzyme substrate complex. Okay. And, oh man, it really is something. And, see, I messed up. If you form the product, the enzyme comes back, right? That's why it's a catalyst. It's not a catalyst if it gets used up, but if it comes back, it can redo its work. That's what makes it a catalyst. Okay, so that means that we have another source of enzyme is when the catalysis has done its job, and the actor responsible for that is the enzyme substrate complex. So the enzyme, notice that the enzyme substrate complex makes more enzyme whether it turns left or right. The main thing is that you can look at these expressions and write these rate things, because if you can do this, then you can, again, use a computer to figure out what the integrated rate expressions are, or in this case, we're going to use the steady state approximation. That's how we're going to do this one. Okay, let's look at the substrate. And let's see, we have a sink, which is the same as for the enzyme. Why wouldn't it be its, how is an E different than an S, right? They're just letters. Okay, so there's a sink, and then there's a source, which is the backward decomplexation of the enzyme substrate complex. Okay, but of course there's not another source because it'll turn into a product. Okay, now we have to do the enzymes. Oh God. Oh, I didn't give myself enough room because I still have to do the product. Okay, the enzyme substrate complex has a source, which is the enzyme and the substrate of, it says plus K1. It has a sink, which is, of course, itself to form product. And, a sink if it goes backwards, and then a sink if it forms product. I got that confused. Okay, so there you go. And the last one, I kind of screwed up. I didn't give myself enough room. The one that we actually care about is, of course, the product only has a source, and that is the enzyme. So that's plus because it's a source. There's only one, and it's the enzyme substrate complex with a rate kcat. Okay. Okay, now what we're going to do is apply, so put a little star in your notes. I'm not going to use the word super well here, because this is going to get a little complicated, okay? Steady state approximation. That's what they did. Now, Michaelis-Menten didn't quite do that. They assumed some kind of equilibrium between the enzyme substrate and ES. Actually, it sounds fine to me, but whatever. Briggs and Haldane use the steady state approximation in what they do for the enzyme substrate complex. And so they said the rate of change is 0. Again, it's considered a little bit more accurate to think of it this way, and that's why I'm showing you. Plus, we can also solve it. Okay. Now, if that's the case, then all this stuff is 0, and this is where it's going to get a little nutty. So K1 ES is equal to K2 plus K cat. Parenthesis, concentration of the activated substrate. Okay. Okay, next one, and I think this is again the free ligand approximation. Maybe I'm getting that wrong. You're going to assume that the amount of enzyme is going to be the initial amount of enzyme, which sounds fine, minus that which is bound in the enzyme substrate complex. Okay. Okay, so now what I can do, and I'll keep working down. Oh God, I think I've already gotten confused myself. Let's see. Blah, 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 blah. Okay. So K1. Okay, so now I'm going to do is I'm going to put E naught minus ES. Sorry, little brackets. It's important. Okay. Okay, then S. So all I've done is I've substituted this in for here. There we go. And this is equal to the same thing. K2 plus K cat. Okay, so there you go. Okay, now some algebra. Let's see here. Okay, so I'm going to just do the algebra. Look, it's a middle school skill. What I'm looking for is the concentration of the activated substrate. So what I'm going to do is I'm going to try to put those together. So you see that this is on both sides. It has two parts. There's the K2 plus K cat. That's on the right, but I moved it to the left. And then I've got a K1 and the substrate, concentration of substrate. Okay, there's that. And then the leftovers are K1, K1 initial concentration of enzyme, and concentration of substrate. There we go. Okay, so that's the leftover. And I've messed around with some minus signs and whatnot. It's a bunch of algebra. Okay, now I didn't do that much algebra, so remember that as like last time, I really need to get to the enzyme substrate concentration because that's what the product is proportional to. Okay, so this is now K1, E at time 0, initial enzyme concentration, substrate over K2 plus K cat plus K1S. Okay. Now, it's a little hard to figure out what to do next. And what you're going to do is divide both the top and bottom. So you're going to multiply by 1 by dividing, boom. It's a lot to take in. Dividing the top and bottom by the same thing. You divide by K1, top and bottom. Okay, so notice what you're going to get. Concentration, initial concentration of enzyme, substrate. Then you've got a really terrible looking thing. This ratio of rate constants plus concentration of S. Oh, I guess there's no need for a parenthesis there. Okay. I know it's a bit to take in. Okay. Now then, this ends up being called enzyme, initial enzyme concentration, S. Okay. Now we've got Km. Okay. Now this, we're almost at the end. It's not that bad, right? It's kind of bad. Anyway, where this differs from Michaelis-Menten is mostly this thing right here. So they call this the Km. They call it the Michaelis-Menten constant. They still call it that. All right? And it's just the ratio of the backward reaction, the forward reaction to the product divided by, anyway, it's just a fraction of all the rates. Whereas before, in Michaelis-Menten, it was the dissociation constant. So that's where it's different. Last bit. So really, it's basically the same thing. And so that means that the way that biochemists like to put this is this rate, which is, of course, K cat enzyme substrate concentration, and that's still going to be expressed as the maximum rate concentration of substrate over Km. Again, Michaelis-Menten and then the Briggs-Haldane expressions they're actually identical. They're identical. So it's like, why am I doing this? I don't know. But the nature of the way that you think about how these things work over time is different. So that's why it's kind of important. And the nature of the constant. When you look up Michaelis-Menten, you're actually looking at this definition of this characterization of the enzyme activity. That's different than the actual what Michaelis and Menten actually did. So it's kind of funny how that worked. Last bit, where this fails. So notice that in both systems there were approximations made. One was that you could think of Michaelis-Menten was that the enzyme substrate complex was in equilibrium, and the Briggs-Haldane, which was that the enzyme substrate could be thought of as being in a steady state. So as soon as, so it takes a while for it to form, but when it forms, it goes away very quickly. And there was also the free ligand approximation. So this reaction velocity, which we know as a rate, as a function of substrate concentration. Let me point out that, okay, here's Vmax again, that it's expected to kind of look like this. This function looks like this curve. But one of the most important thing is, and apparently this is something you actually have to really be concerned about, and I'm not really a biochemist, but I've read enough to know that this is something you have to think about. It's when the free ligand approximation fails, and that's when substrate is not as readily available compared to the enzyme. The free ligand approximation assumes that there's always tons of substrate, and it's the catalyst, the enzyme, that's actually not overly populated. That sounds like a good approximation to me. Proteins are kind of hard for your body to make, right? Regardless, apparently it breaks down a lot, and what happens is you see behavior like this. Looks like that. So that's when the free ligand approximation fails. So anyway, that's what it looks like. I don't think I'll put that, minutia like that I don't put on tests. What really is useful is, in terms of the final, I'll probably ask something about describing the overall mechanism. And as I also said many times, and I'm sure it's on your third test, I haven't written it yet, although you just had it. Remember, I go forward in time, is practicing. I'll still probably put something like this on the final. Being able to look at a mechanism and being able to write the rate expressions. I probably would maybe ask a question about this because it's kind of the only thing I could ask. Okay, so I think we are, I'm double checking, we're going to end a little early because why not? It's the last class. Again, look for the review session to be published, to be posted as soon as I finish it. So I don't, again, this is way in the future. I don't know when I'll have it done, but I will try to have it done sooner than Friday. And as you have seen so many times, I'm going to spill my guts, what's on the final. I write the final first, and then I do the review session. I've done that for all the tests. Look at all of the review sessions for the other tests, and you will know that I tend to do that. Aside from the final review session itself, the review sessions for the other tests will be the things you want to watch. If you're completely freaked out, of course, you can watch the entire class over again. You have that capability. That's why I've been doing this long before COVID, was just in case you really freaking thought, oh God, you have that available to you. You can do that. It's a bit nuts, but it could be done. Other than that, if any of you have any questions, just email me, because since I'm now freed up, I'm now filming the last class 2 weeks ahead of time. I'm actually freed up. So that means I'm a little bit more responsive towards emails right now. So go ahead and email me if you have any questions, and you still have 2 hours of review, so that's not done yet. So I will see you then.